ask you to do it the other way around. So use the standard normal curve table to find the z-score for the given condition. A graph might help understand this. They're saying that 4.01% of the total area is to the left of the z-value. So now what's happening here is that they are giving you the probability, and they are asking you to find the z-score. So 4.041% is to the left of the z. So if my z-score is this value along the x-axis, the 4.01% is the area of this little tail right here. So they're saying that this has area or probability of 0.0401. So rather than going to the outside of the table and finding the probability on the inside, we're doing the exact opposite. We have to go to the inside of the table because the inside of the table is where the probabilities live, and now you're looking for the value on the outside of the table that corresponds to an inside value, an area or a probability value of 0.0401. So now we're looking inside the table. I'm going to zoom in so we can see this. That's as far as it'll go. 0.0401. 0.0401. Okay, I see 0.03s, 0.04s, 0.0401. There it is. See it? So I'm looking for, this is the probability to the left, is 0.0401. What is its corresponding z-score? It's whatever the border of the table is. So that is negative 1.7, and then the second decimal is 5. So it is negative 1.75. That is the z-score. In question 25, it's very similar, but not exactly the same. Because this time they are saying that 25% of the area is to the right. And then there's several ways to think about this. So of course you know I'm not drawing accurately, but I'm doing my best. This means that 25% of the area, so in this upper tail, these are called tails, by the way. They extend out forever. So the area that's in the upper tail, as opposed to the previous example, this one is a lower tail, this one is an upper tail. That's not really much of a tail because it's 25%, but 0.2514 is the probability above the z-value, so to the right of the z-value. So now, what does the table give you? The table only gives you the probability of being less than. So if I look up 0.2514 in the table, that will not give me the right value. So there is more than one way we can approach this. Here's perhaps the most sensible way to approach this. If 0.2514 is above the value for z, since probabilities have to add to 1, that means that this region in here would have to have area 1 minus, or probability, 1 minus 0.2514, which is 0.7486. So that I can either look, I guess that's the easiest thing to do. We should look up 0.7486 in the table because that's actually what the table gives you. The table gives you the probability of being less than some number, I guess I'll call it score. So what z is less than whatever that value is 0.7486, which is equivalent to saying the probability of being greater than that value is 0.2514. Does that make sense? The probability of being less than this number is 0.7486, and consequently the probability of being greater than that number is 0.2514. I shouldn't say equals, but that's what the table, they mean the same thing. So now in the table I have to look up 0.7486. Okay, so I'm finding the 7s in here. 0.74. Hey, I think I just found it. Doesn't get any bigger. 0.7486 appears to be right here. The outside number for that is negative, not negative, 0.67. So the z-score, oops, is 0.67. All right, now let's see if we have enough space to try to do this last word problem. The mean clotting time of blood is 7.35 seconds. So that means that your expected value, so mean is the word that means expected value. And we tend to also write that as mu. With a standard deviation, which we tend to call sigma, of 0.35 seconds. What is the probability the blood clotting time will be less than 7 seconds? Assume the normal distribution. So this is then asking the probability that blood clotting time, which is represented by the variable x, is less than 7 seconds. So now the problem here is that your random variable x, although it is normal, it is not standard normal. Its mean is 7.35. And its standard deviation is 0.35. So, in order to be able to use the table, you need to standardize. Standardizing is done by subtracting the mean and dividing by the standard deviation. I should not have done I did a generalization in here for some reason. I don't want to have to read you this whole thing, so just bear with me. In general, this is how you standardize, because I think it will be helpful to look at the notes. So this x on the left is representing the variable x. It's the random variable. It's this x. But this x1 is a numerical value. It's like your 7. So this is your x. This is a variable representation for the number 7. This could be any number. Variable number. On both sides, because what is happening in these parentheses is actually an inequality. So you can perform calculations on the inside of these parentheses just like you would any other calculation. To standardize on both sides, because again, it's like an equation, it's an inequality, you subtract the mean on both sides, and you divide by the standard deviation on both sides. And by doing this is called standardizing. Once you standardize, you can now use the standard normal table, which is the table we've been using. That is the only table available to you. If you have a distribution whose expected value is not 0 and whose I can't think of the word. Standard deviation is not 1, you cannot use the table. But the workaround for that is to do this standardizing procedure. So back to our example, I have the probability that x is less than 7. The expected value for this particular problem is 7.35. So on the left and on the right, I will subtract the expected value of 7.35 and divide by the standard deviation of 0.35. So now here's the magic. This x minus 7.35 divided by 0.35 is standard normal. So now we start using the letter z, because z is always representing the standard normal. So that means that we now have transformed this into a random variable whose expected value is 0 and whose standard deviation is 1. So it turns out this calculates out quite nicely to be z is less than -1. So now to use the table to find the probability that z is less than -1, lucky for us, the table gives us less than probabilities of less than -1. Okay, so now we're back to the outside of the table because we are looking for the probability that z is less than a value. So I'm looking up the z value, which is what the outside of the table is. So we need -1.00, which is 0.1587. Oops, too small. Okay, and I think we have one more question, but I think I have to pause.